In this lecture, I will just introduce you to the terminology of group representations, some examples, permutation representation, regular representation, and then I'll talk about the direct sum of representations, equivalence of representations, sub-representations, irreducible, reducible representations. So we will develop this terminology. It is basically the terminology. And then in the next lecture, I will connect representations with modules. And then once we have done that connection, and then how the study of modules over group algebra is used in the study of representations, I will discuss that, and how irreducible modules correspond to irreducible representations, sub-modules correspond to sub-representations, and so on. And then I will say something on the characters of the group and the character table. So that is what plan is. So let's start with the terminologies. So what is a representation? As I have told you that if for us all groups are finite, so because I am just discussing representations of finite groups, G is a finite group and F is a field, and a representation of G over F is a homomorphism from G to G ln F for some n greater than or equal to 1. And this n, the size of the matrices, this is called the degree of the representation. So let me tell you, when the field changes, the representation theory completely changes. The representation theory of a group over complex numbers is far different from its representation theory over rationals or over reals. If the field is algebraically closed, for example, say complex numbers, representations are easier to handle, easier to understand. The theory is much refined as compared to the representations when the field is small. So this field is very important when we are talking of the representations. So in the beginning, I will talk of representations over a field, but then later on, I will specialize to representations when the field is, say, complex numbers or any algebraically closed field. Then we will have a better understanding of these things. So what is a linear representation? A linear representation is that when n is 1. So it's a homomorphism from G to non-zero multiplicative group of a field. So linear, so a homomorphism from a group G to a non-zero elements, so GL1F. GL1F means non-zero elements of F, which is a group under multiplication. So any homomorphism from G to non-zero elements of a field is a linear representation of G. Examples. So you can have trivial representations, of course, trivial representations of any degree. So I can send G to the n cross n identity matrix, all group elements to n cross n identity matrix. I get a representation of identity representation of degree n. And trivial representations of degree 1 are just called trivial representations. So let's try to write down some representations of cyclic groups. So let's try to write down degree 1, and then others I will just say on that. Suppose you have a cyclic group of order n, and suppose my field is, say, complex numbers. Then I'm writing homomorphism from G to non-zero complex numbers. And so this is the generator of the group. All you have to know is, where is generator going to? So this element A is of order n, and this is to be a group homomorphism. If I can send A to something, then of course I will send A to the I to the same thing to the power I, because I want this to be a group homomorphism. Now, because A to the n is identity, and then so this, if A goes to zeta, then zeta to the n also has to be identity, because you want this to be a group homomorphism. So basically you can send A to any nth root of unity, And what you get is a homomorphism from G to non-zero complex numbers. And these are linear representations of G over C, complex numbers. So if you have a field F, then you should have a root of, you can map A to a root of unity, nth root of unity inside F. If it exists, then you will get a linear representation over F. And now you can blow the sizes. For example, I don't know why I actually wrote Z mod NZ first. So A was the generator. So the generator of the group, you send it to. Now I have set some nth roots of unity on the diagonal. And basically you can send A to any matrix whose nth power is identity. So this can be any matrix A whose nth power is identity, and then it will give me a homomorphism from G to GLM C for any size M. But then I will come to reducible, irreducible, and it will come to you that this is a sum of linear representations, degree 1 representations. Okay. So let's say I want to write down linear representations of clients for group. Then basically I have to give you a homomorphism from say let's say complex numbers over complex numbers. I have to give you homomorphism from Z2 cross Z2 to C, and the generators of Z2 cross Z2 are this. So so the elements of Z2 cross Z2 are this. So basically you have to see where are the generators going to, and A is of order 2. So A I can map to anything whose square is 1. So I can map it to plus minus 1, plus minus 1. And the relators, these relations should be satisfied, and which are satisfied for these elements. So these are representations. A goes to plus minus 1, B goes to plus minus 1. Then I get 4 representations. A goes to 1, B goes to 1, A goes to 1, B goes to minus 1, and so on. Those 4 choices. And then I get 4 linear representations of this Klein's 4 group over complex numbers. And say if you want a field, then you should have a second root of unity in that field, and then you can have a linear representation. Otherwise, you will have to map A and B to both 1 and 1, and you will only get identity representation over that field. So let me come to say dihedral. Say I am having
Gurmeet, there is a repetitively one person one question is there.
Yes.
Group action and permutation representation is same as group representation. That is the question they are asking. Permutation representation in intermittent foot means that after group action we have that embedding.
Action gives you group action gives you representation. Yeah. I will describe that.
Okay, so yeah.
Group act with, if you have a group acting on a set X, then you have a representation of G on a vector space with X as a basis. I will come to that. Wait a minute. I will come to that. So so these are so I've just taken dihedral group. I've just taken a dihedral group, and let's try to write down linear representations of, say, this dihedral group, Dn2, say, over complex numbers. Now A goes to something, B goes to something. Now you have to decide what this something is so that it's a homomorphism, and all you have to have is that A and B should go to something which satisfies these relations. These relations have to be met. Suppose I send this to alpha, I send this to beta, say instead of AB, then I should have alpha to the n is 1. Alpha is the nth root of unity. Beta is plus minus 1. Beta square is 1. But then other relation, B inverse, AB is A inverse. Because it's a homomorphism, you will get that alpha and beta should have this relation also. So which will mean that because alpha and you are having linear representations, alpha and beta are in non-zero complex numbers, they commute. So that means alpha is basically alpha square is 1. So alpha is just plus minus 1. So the only choice of homomorphisms from Dn to non-zero complex numbers is this. A goes to plus minus 1, B goes to plus minus 1. So you get these representations. Okay. So let's talk about dihedral group of order 8, and let us try to construct a 2-degree representation of a dihedral group of order 8, D4. So how do you view D4? I will put my this thing on charging. Okay, so let's say this is your dihedral group. You can view it as the group of symmetries of a square, right? So this is my 1, 0. This is my 0, 1. Okay, other entries you can write accordingly. And this is minus 1, 0 and 0, minus 1. Now, I have to decide, I'm going to write down a 2-degree representation of D4 from GL to say C. So I should decide where A and B can go to matrices A and B. Basically, A and B can go to matrices A and B, which satisfy the same relations as those of the group. If that happens, then there is a homomorphism from D4 to GL2C, because D4 is you take free group on 2 generators and divided with the normal subgroup generated by the relations. So because of that, so all you need is that A to the 4 is 1, B square is 1, and B inverse AB is equal to A inverse. And you can achieve these relations by the group action, because look at the D4 is the group of symmetries of a square. So I can take 4 order element as the rotation through angle pi by 2, and 2 order element in D4 by reflection through, say, this diagonal, and those are the 2 generators. So A I can take as rotation through pi by 4, and B I can take as the reflection through this diagonal, say. Okay, reflection through the diagonal. Now, if you look at linear transformation from R2 to R2, from R2 to R2, you look at the linear transformation by rotation through angle pi by 2. Then what is that linear transformation? Where is 0, 1 going to? So what are the bases? How do you write linear transformation? You have to send bases to bases, and then what you get is a 1, 1 on 2 transformation from this to this, and matrix of that will be an invertible matrix. So basically, rotation through pi by 2 is that I send 0, 1 will go to, sorry, 1, 0 will go to 0, 1, and 0, 1 will go to minus 1, 0. So I can map to, so 1, 0 is going to 0, 1. So the matrix which I am going to get will be this. This will be the matrix of linear transformation, which is given by rotation through pi by 4, and B goes to B. I am taking as the reflection through this diagonal. So this element will come here, and this element will come here. So 1, 0 will get mapped to 0, minus 1, and 0, 1 will get mapped to minus 1, 0. So if I look at this linear transformation of R2 to R2, then this is a representation. So I'm sorry, this I have to take from G to GL to R. I'm getting over R, over reals. So there's a representation. This is a homomorphism from dihedral group of order 4 to GL to R, given by A going to this matrix, B going to this matrix. So you're representing the elements of dihedral group by matrices. And what you get is a representation. And this you obtained because the dihedral group was the group of symmetry of a square. And so you obtained as a linear transformation from R2 to R2. And you took the matrix of that linear transformation. And instead of rotation through pi by 4, I can also take rotation through minus pi by 4. Then my representation will change, but then I will prove that you can prove that these are equivalent representations once I define the concept of an equivalent representation. Now, if I take a rotation through minus pi by 4, then 1, 0 will go to, instead of this matrix, I will get 1, 0 will come to 0, minus 1. So I will get this. And where will 0, 1 go? 0, 1 will come to 1, 0. Whereas this matrix, I'm keeping the same diagonal, or you can also change the diagonal. So then this matrix will also change, and this is another representation, but by changing the basis, or you are not going to get any new representation. These are equivalent. At the moment, it's looking a different representation, but they are equivalent. I will come to the concept of equivalent of a representation. So this is how group actions are used in representations. And soon I will define representation with a representation space, and then I can, in general, say if you have a group acting on a set X, then you can have a representation of G. So far I have defined representation of G as a homomorphism from G to GLNF. Okay. So, but GLNF is what? GLNF is isomorphic to, you take an n-dimensional vector space over F, take V to be a vector space of dimension n over F, and GLV is the group of automorphisms of V, all 1, 1 onto linear transformations from V to V. That's a group. And you also take the group of n cross n invertible matrices over F, which is GLNF, and then these two groups are isomorphic. So, how are these two groups isomorphic? That comes from your, how can you prove that these two groups are isomorphic? It comes from your linear algebra course. Describe this isomorphism between GLV and GLNF. Once you know this isomorphism, then I will keep on switching easily from, if I have a linear transformation from G to GLNF, then I'll say I have a linear transformation from G to GLV and vice versa. So let us just...
There are some questions from the previous example, D4. Yeah. So one person says rotation should be pi by 2 or pi by 4. The D4...
Sorry. Yeah, pi by 2. Yeah. Pi by, yeah. I'm sorry. Yeah. I think I said pi by 4.
I don't know. I thought it was pi by 2 only, you said, but
pi by 2. It's pi by 2. I'm sorry if yeah, that's just a slip of tongue. I'm sorry, pi by 2.
And Prem asked, every group action gives a group representation. That is a question mark. So yes. Yeah.
Yes. We can define that. I will do that in this terminology. Is that okay?
Yes, you can go ahead. I think you answered all their questions.
Yeah. So let us describe this isomorphism from GLV to GLNF. I'm just doing everything from the scratch so that if there are some fresh master students, they are able to connect the things with what they know. So this is what you learn in your linear algebra course, that this endomorphism of V, and what you understand what is endomorphisms of V, all linear transformations. V is an n-dimensional vector space over F. Endomorphism V is all linear transformations from V to V over F. May not be 1, 1 on 2, but all linear transformations from V to V over F. This is a ring. You can add two linear transformations, you get another ring, and you can compose two linear transformations. That is another linear transformation from V to V. So that is the multiplication, and this becomes a ring. And this ring is isomorphic to, this is the basic thing which you do in your linear algebra course, that this endomorphism of V is isomorphic to the ring of n cross n matrices over F. And how is this isomorphism done? And then by restricting that isomorphism on invertible linear transformations, you get isomorphism from GLV to GLNF. So if you recall, how is this isomorphism done? You look at basis of, take a basis of V as a vector space over F. Now, for every linear transformation T from V to V, there is a notion of the matrix of T relative to T, denoted by, which I will denote by the matrix of T relative to B. Just recall this notion because I will be using that. How is this defined? How is this obtained? You apply this linear transformation on basis element and write it as a linear combination of basis element, which is allowed, which is possible because that's a basis. And then you have TV2, you write it as and so on. And similarly, you have TVN. Now this matrix Aij is called the matrix of, so whatever coefficients you get, you apply that on the, put that in the first column of the matrix. Whatever coefficients you get, when you compute TV2, you put that in the second column of the matrix. And that is what my notion of the matrix of T relative to B is. This you prove in your this mapping theta from endomorphisms of V to n cross n matrices over F by mapping T to matrix of T relative to B. I have fixed B is the ring homomorphism. It is 1, 1 and on 2, and therefore it is an isomorphism, and therefore endomorphisms of V become isomorphic to n cross n matrices over F. And you have also proved in your linear algebra course that T is 1, 1 and on 2 if and only if the matrix of T relative to any basis you take is an invertible matrix, right? Therefore, by restricting T on 1, 1 onto linear transformations, that means on the unit group of the endomorphism ring, what you get is a homomorphism from an isomorphism from GLV to GLN. So all 1, 1 on 2 linear transformations from V to V over F are in 1, 1 correspondence with all invertible n cross n matrices over F. So therefore, I can define a representation as a homomorphism from G to GLV, where V is a finite dimensional vector space over F. So, and what will be the degree of the linear transformation? It will be the dimension of, because the degree of the linear transformation was n, the size of the matrices. And what will be the size of the matrices? As much as the dimension of V over F. So the degree of, if I write representation like it's a homomorphism from G to GLV, then degree of the representation will be the dimension of V over F. Okay, so all right. So that means if I have a representation in this form, if I have a representation T with the representation space V, then how do I get this representation from G to GLNF? By just this, if this representation is G going to TG, then this representation is G going to, in the matrix form, I will write TG, and I have to choose a fixed basis B of the vector space. And then if I compute matrix of TG relative to the basis B, then this is in the matrix form. And conversely, if T is given this in this form, where G going to say AG, then I have to take the corresponding T from G to GL. V, I can now take V as Fn, n-dimensional vector space over F. So I will take V as Fn, and G will go to TG. TG is linear transformation whose matrix with respect to, say, canonical basis is AG. So you can write down, if AG is your AIJ, so you can write down what this TG is. Now TG is such that the matrix of TG relative to this basis is your given. So I can go from this side to this side, this side to this side. So I will keep switching between representation in with the vector space or representations in the matrix form. Now, let me define permutation representation. So what is permutation representation? Say, these are defined for Sn. I will first define it for Sn, and then I will define it with the group action also. Suppose your group is Sn. Okay. Now I take a vector space with bases V1, V2, Vn. Sn acts on 1, 2, 3 up to n. Right? Sn is an action. Sn acts on 1, 2, 3 up to n. So I've taken a vector space with bases V1, V2, Vn, and I set sigma. So what is the homomorphism from G to GLV? Sigma going to, sigma is in Sn, sigma going to T sigma. How is T sigma defined? T sigma, I want this to be a linear transformation from T sigma should be 1, 1 onto linear transformation from vector space V to V. Now V is with basis V1, V2, Vn. Okay, so it is enough to define this on basis elements. So in order to define this linear transformation from V, it is enough to know where are basis elements going to. So I say V1 goes to V sigma 1, V2 goes to V sigma 2, and Vn goes to V sigma n. Okay, so this is a 1, 1 onto linear transformation from V to V, because I'm sending basis to basis. This linear transformation will remain 1, 1 onto. And so this T sigma is an element of GLV, and it's a homomorphism you can check. And therefore, it's a representation of Sn. And this is called permutation representation of Sn. What is its degree? Its degree will be n. Because it is the dimension of V as a vector space over F, its degree is n. Now, if instead I can just improve this permutation representation, say I have a group acting on a set X. So I will I will first explain permutation. Suppose I have a group G acting on, suppose a group G acts on a set X. Okay, so my set X is say X1, X2, Xn. Now I can take a vector space with X1, X2, Xn as a basis. And then I can define the same way as the permutation representation. Define map from G to GLV by sending G to TG, where what is TG? TG is linear transformation which sends Xi. Xi, where will Xi go to? The action of G on Xi. The group G acts on the set X. So action of G on Xi, it's some new Xj. So that is what the linear transformation is. And then it gives you a representation of G. Representation of G of degree, how much? Degree as the size of the set X. If G acts on a set with M elements, then with this I get a representation of degree M. Okay, so somebody asked this question about group actions, and is that clear? Or if there is any doubt, I can still answer.
Yeah, I think 2-3 were asking the same question.
Okay. Yeah, so that way, similar to permutation representation, it is one example of a representation from a group action, because Sn was acting on 1, 2, 3 up to n. So this notion can be generalized to representations coming from group actions. Now, say what will be this representation in the matrix form, permutation representation in the matrix form, say. So let's try to understand how do you write down. Say I want to write down a permutation, say let's write down image of some 1 or 2 elements so that it is clear to you. Say let's say I am talking of S4. I am talking of S4. Then I will get a representation of degree 4. Say I am talking over complex numbers. Now in this representation, say I want to see where is 1, 2, 3 going to. 1, 2, 3. 1, 2, 3 is going to. Now the linear transformation which you are going to get from 1, 2, 3 is that V1 goes to V2. If V1 goes to V2, then the first column will be this. This is, I told you, how do you write matrix of a representation from a linear transformation? You compute it on basis, write it as a linear combination of the bases, and then put the coefficients in the columns. Okay, so because now V1 goes to V2 in the sigma takes V1 to V2, so this will be this, and then now V2 goes to V3, V3 goes to V1, and 4 is kept fixed. So this is the matrix what you are going to get. So where will 1, 2 into 3, 4 go to? 1, 2 into 3, 4 will go to 1 goes to 2 and 2 goes to 1. 3 goes to 4. So this will be the column, and 4 goes to 3. So this way, right? So this way you can write down homomorphism from Sn to GLN. See, you can write down the image of any element. So what's a regular representation? Regular representation.
There is one question. If we have a homomorphism G to GLV where V is infinite dimensional vector space, do we call it representation? Surojit.
Yeah. Those are representations infinite dimensional. So yes. But I will be talking over representations over finite dimensional vector spaces only.
Yes, you can.
Okay. So this is, I am going to define regular representation. Regular representation is that you take a finite group G and look at the group algebra FG. I have to define with you. I think these students may not be familiar with the group algebra. Okay, so yeah, so you just take, I just need to, you take a vector space with G as a basis. So this is your G, G1, G2, Gn. So you just take F linear combinations of these elements of G. So you form these elements, formal F linear combinations of elements of G. So basically you are taking vector space with G1, G2, Gn as a basis. And as of now, I'm not going to give any this ring structure, but I just look it as a vector space over it. So later on, I'll tell you that this is a ring, and then we'll study modules over this ring and so on. But just look at all F linear combinations of elements of G. It's a vector space over F. Okay, by using the multiplication of the group, you can easily give a ring structure to this FG. It's called the group algebra of G over F. And so if you look at this vector space FG, then you look at this mapping from G to GLV by mapping G to TG. Now, what is TG? TG, you have to define TG as a linear transformation from V to V over F. So basis elements, as I said, basis elements are group elements. Say H is, suppose H is a group element. Where do I map H to? I am mapping H to G times H. This is another group element, which is another element of the basis. So basis is going to basis. It's a 1-1 onto linear transformation from V to V. And you map G to TG, and this is a well-defined homomorphism, and it's called a regular representation of G. Regular representation of a finite group G. So what is the degree of the regular representation? It is as much as the order of the group, because the dimension of the vector space V over the field F is the order of the group. So as much as the order of the group, this is what the degree of this representation is. So let's say a regular representation in the matrix form, what will be this? So if I write down representation in the matrix form, then it will be G to GL and F, where G is going to the matrix of TG relative to B. TG is the same. If you remember, TG of GJ is GGJ. So the matrix will be, so the matrix of TG relative to the basis B will be Aij, where this Aij is what? 1 if GGJ is GI and 0 otherwise. So this is the matrix you are going to get. So let's say regular representations of cyclic groups. So let's write down regular representation of a cyclic group in the matrix form. Say T. So it will be of order degree n, GL and F. Now, I just need to write down where is A going to, because it's a cyclic group. Now, where will A go to? Now, TA is going to map 1 to A, meaning the first column will be this. A is going to A square. So this is the second column, and this is the last second column, and this is the last column. So it's a circulant matrix, so which came in the morning. So a regular representation of cyclic groups, A is going to this circulant matrix. So let me call this by capital A. So maybe you can try writing regular representations of say dihedral group DN or D2N, whatever you call. You can write down regular representations as an exercise. Now let me come to sub-representation, concept of sub. So I have defined with you what a representation is in the matrix form and in the vector space form, and they are just the same. You should know how to go from one to other. And now I am going to define sub-representations. Representations of, like you talk of the concept of subspace, subgroup, subring. So you also talk concept of a sub-representation. So basically, as the natural, so I have a representation is from G to GLV. So basically, G going to TG. So I will restrict this linear transformation on certain kind of subspaces. So let me just go through this. Suppose V and W are two vector spaces, then you know the concept of direct sum of two vector spaces. And the dimension of the direct sum is the sum of the dimensions. And then I will view V as a subspace of V direct sum with W by viewing V inside V as the tuple V0. And I will, so a basis of V and a basis of W if I take, and I take their union, then that will be a basis of V direct sum with W. Now, suppose you have a linear transformation of V and a linear transformation of W. Suppose I have a linear transformation of V and a linear transformation of W, then I can talk of the linear transformation of V direct sum with W by this obvious map. V on the first component you apply T, and on the second component you apply the linear transformation on W. And if T and S are 1, 1 on 2, then T sum S is also a 1, 1 on 2 linear transformation from V direct sum with W to V direct sum with W. And if you compute as I told you, if B and B dash are bases of V and W respectively, then this is a basis of V direct sum with W. And if you compute matrix of T relative to this basis, then it is this, these two on the diagonal and 0 elsewhere. So I will need this representation in the matrix form. So this is how direct sum of representations is defined. G going to TG sum SG. TG is a linear transformation from V to V, 1, 1 linear transformation from V to V, SG is from W to W. So TG sum SG is from V direct sum with W to V direct sum with W. And this is a well-defined homomorphism, and it gives you a representation of G on a representation space V direct sum with W. So I'm sorry, I'm first telling you direct sum of representations, and then I will come to sub-representations. So this is direct sum of two representations. So this is T, this is S. Then the direct sum of two representations is a representation of bigger degree on it's with representation space V direct sum with W, and with this definition. So in the matrix form, what I am saying is that if I have G to GL and F, this is one representation, and other representation is from G to GL MF, then what you are saying that you have this mapping from GL N plus MF by mapping G going to say G going to say AG here and G going to say BG here. Then in the matrix form, all I am saying is that you look at this matrix. If AG and BG are invertible N cross M and M cross M, then this is an invertible matrix of size N plus M cross N plus M. This is what I am saying, that you just blow up the sizes and then you get direct sum of two representations. All right. Now is concept of equivalence of two representations. Okay.
Gurmeet, before that, actually, there is one question from Sirisha. I mean, she's asking us you to repeat the regular representation. Is it possible for you to explain again?
Yeah, sure.
Yeah.
She wants that, definitely. Regular representation. This one?
Yes. She wants the definition, I think, again. Yeah.
So, yeah. So you look at G is a finite group. You look at vector space with the group elements as bases, right? So you just take formal F linear combinations of group elements. Say if your group is say S3, you just take, and suppose your field F is complex numbers, then what I am saying is that you look at CS3. CS3 means lambda 1, S3. So this is the identity element of S3, then lambda 2 times the next element, and lambda 3 times 1, 3, lambda 4 times 2, 3, lambda 5. I'm sorry, this is too much of, I need to erase this. Lambda 5 times 1, 2, 3, and lambda 6 times 1, 3, 2. So you look at all C linear combinations of group elements, whatever your group is. This is just an example of S3 I've written. Whatever your group is, you take the C linear combinations of those elements. So you get a complex group algebra. So similarly, you just take formal F linear combinations of those group elements, you get a vector space over F. Okay, I'm not saying it's a ring or anything at the moment. That's a vector space over F. And now you look at the mapping G going to TG. Now, how is, see, this is what you have to define. That is what you're doing in, where is this, what is this linear transformation? I say this linear transformation, see, it is enough to define a linear transformation on a basis elements. So these group elements are basis elements of this vector space. V is formal F linear combinations of group elements. Group elements are basis elements. So I say you map H to GH. For example, if I'm having this, say F is C and you are in S3. So what I am saying, say if I am writing what is T of 1, 2, T of 1, 2, 1, the identity of this S3 will get mapped to 1, 2, and then 1, 2 will get mapped to 1, 2 into 1, 2, which is identity. 1, 3 will get mapped to 1, 2 into 1, 3, and so on. 1, 3 will get mapped to 1, 2 into 1, 3. So TGH is GH. Right? So this is the mapping, and this is called, this is a homomorphism, and this is called regular representation, actually. If that is clear. Can I move?
Yes, yeah, you can.
So yeah, so I am just talking of the concept of equivalence of two representations. So when do you say that these two representations are equivalent? So you say that these two representations are equivalent if you can obtain one from the other. Suppose I have an isomorphism from V to W in such a manner that this homomorphism can be recovered from this homomorphism by some means, then I will say that these two are equivalent. So what you're saying that these two representations, there's a representation with the representation space V, and this is with representation space W. If there is an isomorphism from V to W such that, now what is SG? SG is a linear transformation from W to W. So what you are doing, phi inverse is from W to V, and then from V to V you have TG, and then from V to W you have phi. So if SG is equal to phi composed with TG composed with phi inverse for all G in G, then you say that these are equivalent representations. These two are equivalent representations. So the first thing is that equivalent representations must have the same degree, because you are getting an isomorphism between those two vector spaces with this additional property that there is a connection between. So you can obtain this linear transformation SG from TG via conjugation with this phi. Then you say that these two linear transformations are equivalent, right? So what do I mean by equivalent linear transformations when I have them in the matrix form? So what will I write? So these two linear transformations, this and this, are equivalent. So you think of, now you have a way to move from one to the other. You have to take the matrix with respect to the basis. So what do you get is that if you take the analog of what I have written here, if these two are equivalent, if these two are equal, then their matrices will also be the same, and which will give me that this should be the criteria for the equivalence, that this here I have G goes to TG and G goes to SG. So basically, so this matrix SG is conjugate of TG by some invertible matrix, but this should be true for all G in G. So this matrix U is independent of G. So if you can find a U invertible n cross n matrix over F independent of G such that TG is obtained from SG by conjugating with U, then you say that these two representations are equivalent, and equivalent representations must have the same degree, which follows from your because there is an isomorphism from phi to W. Now, so suppose I have, this is one basic example which you get is that if I have a representation from G to GLB and then I write their matrices form by taking two different bases. Now, if I take a matrix form of this representation, this T is from G to GLB, and I obtain its matrix analog G to GLNF by sending G to matrix of TG relative to a basis B. I've fixed a basis B of B. Now someone else has taken another basis B dash and obtained this representation. Then matrix of this representation, if I change the basis, will change, but then this is conjugate of this by the matrix of change of basis from B dash to B. That you have proved in your linear algebra course that if I change the basis, then the matrix of TG relative to B dash is equal to U inverse matrix of TG relative to B times U, where U is the matrix of change of basis from B to B dash. Now, this is independent of G. This has nothing to do with G. So these two, if I change the basis and get two matrix forms of one representation, then those two are equivalent representations. So you're not going to get anything new up to equivalence. For example, I wrote regular representation of a cyclic group. Regular representation of a cyclic group. A is going to this circulant matrix. A is going to the circulant matrix. Okay. Now, you look at U, which is the Vandermonde matrix, take all nth roots of unity, zeta 1, zeta 2, zeta n, and form this matrix, zeta 1 raised to n, zeta 2, zeta 2 square, and zeta 2 raised to the n, zeta n. Zeta i's are all nth roots of unity in C. This matrix is an invertible matrix called Vandermonde matrix. And if you calculate UAU inverse, then it is zeta 1, zeta 2, zeta n on the diagonal. So this representation is equivalent to this representation, G to GLNC, which is A going to zeta 1, zeta 2, zeta n on the diagonal. And this is, this is direct sum of these one-dimensional representations of this G. A going to zeta I. A going to zeta I is a one-dimensional representation. And this T is a direct sum of these representations. And this regular representation is equivalent to direct sum of these n linear representations. And this is coming from the determinant of the circulant matrix factors into product of n linear factors and each linear n linear factors and so on. So it is connected with that. I don't have time. It looks like I am not able to finish. Okay, I have not even reached sub-representations. Can I continue for 10 minutes or something?
Maybe you can take actually, because we started late, no? So maybe.
started
Yeah.
late. So I
Right.
think,
We started at 12:07 only, so you can go for
yeah,
another
so I can take 10,
5-10 minutes. Yeah.
right. So that I just finish these notions, and tomorrow I will give them the connection with modules and semi-simple theory and all
Yes.
that.
Yes. Yeah.
Yeah. So what's a sub-representation? Now you have if V is a vector space, V is say I'm taking finite dimensional vector spaces over F. And suppose I have a linear transformation from V to V. Now, if I restrict linear transformation on a subspace W, then it is not necessary that I am going to land in W. Okay, so you say that W is T invariant if T of W is contained in W, so that by restricting on W, you get a linear transformation from W to W. So W subspace of V is called T invariant if T of W is contained in W. So if I have a T invariant subspace, then by restricting on W, I'll get a linear transformation from W to W. And of course, if T is 1, 1, this will stay 1, 1. And now I'm taking finite dimensional. This will, if it is 1, 1, it will also be onto because I have the same dimension. So if I take T in the endomorphisms, say T in GLV, say if I have a T in GLV and W is T invariant, and I restrict T on W, it will be a 1, 1 onto linear transformation from W to W, right? So that is what the next notion I am going to define, sub-representation. Now, T is a representation from G to GLB, not GLNB. So GLNF or GLB. So T is from G to GLB. This is a representation. And W is a subspace which is G invariant. When do I say that W is G invariant? Now let me define. So here is T a representation. T is from G to GLB. W a subspace of V is called T invariant or G invariant. It is called both ways, T invariant or G invariant. If TG is a linear transformation from W to W, so it takes W to W. TG of W is contained in W for all G in G. So what I get is that if W is T invariant or G invariant, then TG restricted on W will be a 1-1 onto linear transformation from W to W. And so this notion makes sense. This mapping makes sense. If W is a subspace of V, which is G invariant or T invariant, then this mapping G going to TG restricted to W makes sense. It's a well-defined map, and it's a homomorphism from G to GLW, and it's a representation of G with representation space W. So you are getting a representation of a smaller degree, and it's called a sub-representation of T. Okay, so its matrix analog will be what? That suppose I take a matrix analog will be that I have to take matrices with respect to some basis. So suppose I take a basis of say W, and I extend this to a basis of V. So I extend this to a basis of V. Now, if I calculate the matrix of TG relative to this basis B, then the matrix will look like this, because T of W1 is a linear combination of W1, W2, WT only. T of W2 is a linear combination of these. T of W2 is a linear combination of these. T of W is contained in W. TG of W is contained in W for all G. So because of this, the first m columns will be, you will be getting zeros beyond this. So the matrix will look like this. So our aim is to go to close to the block diagonal matrices. That is what the aim is. So this is the notion of an irreducible representation. Our representation is called irreducible if the only G invariant subspace of V are 0 and V. So these are the only two G invariant subspaces of. Okay, then you say that your representation is irreducible, and otherwise it is called a reducible representation. G invariant subspaces or T invariant subspaces I have defined with you. So if you have a reducible representation, then basically what you have is that there is a, suppose you are in the matrix form. I'm telling you side by side both the things so that whatever context you study, it should be clear to you. So suppose you have this representation in the matrix form, then what I'm saying by a reducible representation is that there is a matrix U, invertible matrix, such that U TG U inverse is like this. It's a block upper triangular. These are blocks. This is M cross M, and accordingly you compute the sizes now. And this U should be independent of this G. There is a U such that when you conjugate TG with this U, you should get these block upper triangular matrix, or you can similarly talk of the lower triangular edge. So regular representation of a cyclic group is reducible. Why is regular representation of a cyclic group? In fact, regular representation is always reducible. We will see that. But since I just computed it with you, that you remember, for a cyclic group, the regular representation was like A going to the circulant matrix. Okay. And then we proved that 0, 0, 0, 0, 1 and 1, 0, 0. We proved that this representation is equivalent to, so this matrix was conjugate to zeta 1, zeta 2, zeta n. So this is a reducible representation. Okay. So a completely reducible representation means that whenever there is a subspace of V which is T invariant or G invariant, then there is another subspace which is T invariant such that V is equal to, V is direct sum of W and W dash. So basically, so T is completely reducible means that it is equivalent to a direct sum of two representations of smaller degree. So completely reducible representation, you are decomposing that representation as a direct sum of two representations of smaller degree, because if these two are both are G invariant, then the matrix of TG relative to, say, so you take a basis B of W and take a basis B dash of W dash and then compute this, then the matrix will look like something here, something on this block, and 0 here, 0 here. So this representation is made up of, is a direct sum of two sub-representations. Then you say that it's a completely reducible representation. So I think I will stop here, and then I will tomorrow I will define connect representations with modules, and then we will see the semi-simplicity of the group algebra, AFG, Master-Case theorem, when is it semi-simple, and so that when can you decompose your module over FG into direct sum of irreducible submodules, and then we will give the connection that how can you decompose a representation into a sum of irreducible representations, of course, with constraints on the field F. So I will stop here.